But unfortunately, another person didn't make it back, and that was Sydney. Sydney is too tired, and he needs to go back to his room, and so he cannot be here. So instead of one biologist, we have found two biologists in the audience. There's Daniela Rhodes, who is an NTU professor, and David Lane. You're a visiting professor. Is that right?
Yes, sort of. I'm the chief scientist for Space Government.
Oh, sorry. Oh, you see, this is okay, I apologize. But so rather than having long introductions, which I can't do anyway because I don't know David Lane at all, but I think we should start with questions. So who is brave enough to raise his finger for the first question? Oh, let's go. Yes, the gentleman over there. Oh, by the way, we have two people at the sides with microphones. So, or three. That's right. So if you want to raise a question, ask a question, look at the person. I will assign the microphones to you. But go ahead, sir.
Hi. Well, thanks for the talk, Professor Barrows. While we have the privilege of having cosmologists and biologists in the panel, my question is, are we alone in the universe? And if it is truly so difficult to find the existence of other life in the universe, should we give up? And leading to that, if we are truly unique in our own bubble of our universe, is there anything we can do? Is there anything we should do to make sure that we evolve and survive for another 14 billion years?
No, yes, and yes. Are we alone in the universe? Oh, gosh. I don't know if we're alone in the universe. When people talk about life in the universe, I think it's inevitable that there's simple forms of life, bacteria and so forth, that may even be on the moons of outer planets and so forth. Likewise, I suspect there are equally interesting forms of life deep, deep in the oceans and in other exotic environments on Earth. And I sometimes think money would be better spent exploring these local environments exhaustively, before one spent so much going to other places. I mean, astronomers don't don't go searching for life and nothing else. It's usually a byproduct of another mission. So, for example, the SETI search for radio signals generally happens in the background time of other radio observations. So observations taken for other purposes are scanned automatically for interesting signals. There's long been this Fermi paradox, that where are they? That it's hard to think why the universe should be so empty of life. And Kardashev and others in the 1950s put forward these arguments about different classes of civilization, where advancement in civilization went hand in hand with more and more waste energy. So if we've learnt to manipulate our environment on the scale of large lumps of material, we make buildings, we re-engineer coastlines, some people even create new islands in the South China Sea and things like that. But the next level of sophistication for a culture might be that they are able to manipulate their solar system. This might be in simple ways like deflecting asteroids and so forth, or changing the evolution of stars. And then Kardashev thought that maybe if you went one beyond that, if you could manipulate an entire galaxy and its energy sources at the center, then the amount of waste energy you would make you even more visible. My thinking about this is a complete opposite. So I think that the more advanced you become, the more nano, the more microscopic your engineering and technology needs to be if you're going to survive in the long, long, long run. And we see that on Earth. We become more nano in our engineering. if you want to have smaller waste products, smaller impact on the environment, you want to become smaller and smaller and smaller. And so the most advanced civilizations and forms of intelligence in our galaxy and beyond may be imperceptibly small in their impact on the universe. Their space probes may be clusters of atoms and molecules. We just wouldn't see them. So, it could be that we are overwhelmed by thinking that people would do dramatic, big, energetic things like the Empire in Star Wars. But, maybe they're more like ants and small bacteria and do things that have a very small impact on their environment. They don't consume their resources very rapidly at all, and so they last a very, very long time. My favourite explanation for the Fermi paradox, though, why don't we see lots of examples of life? I don't think advanced civilizations last very long. That either they kill themselves off, through internal problems of disease and nuclear waste and environmental impact and so forth, or more likely they're wiped out or their clock is set back to zero by asteroidal or cometary impacts. So the frequency with which they will occur is quite high. And if you have not developed the technology to deflect these oncoming objects, then you run the risk of your evolutionary clock being set back to zero all the time by catastrophic impact consequences. Our solar system has a very unusual structure that has protected us a bit from this. We have a huge giant planet in Jupiter on the outskirts that almost became a star. And when objects get into the outer solar system, it's hard to get past the gravitational pull of Jupiter. In, I think about, was it 2000 or a little before, we observed a comet being captured by Jupiter. Had Jupiter not been there, that comet would have come into the inner solar system. And if it was captured by the sun, it would then orbit the sun, and we run the risk of encountering it again and again and again as it goes round. So the other protector that we have is the moon. The moon is huge by the standards of moons. So compared to the size of us, the Earth-Moon system is a bit like a double planet. And the moon plays a key role in climate control, stopping our climate becoming rather chaotic over hundreds of millions of years. But if you look at the surface of the moon, you can see the other thing it does. It gets hit a lot by stuff that would otherwise hit us. Most of those impacts were early on. So we have this double shield which protects us from impacts. Even so, the dinosaurs supposedly were written off by a catastrophic impact. In 1905, there was a cometary impact in Siberia that was pretty dramatic. And just a few years ago, we saw these news pictures again in that part of the world, Siberia, of this impact from a very large part of a celestial object. And the Vatican's records show that there was another impact in South American forest in the 1920s that missionaries, Catholic missionaries, recorded. So that's a lot of impacts. People started worried when you looked at these records. Once in a few 100 million years, okay, but suddenly you found 3 impacts in 100 years. Okay.
Okay.
Yeah, it's a great question. I think we all speculate, but what was interesting today, was to realise the preciseness of the conditions that have allowed life to develop, and the numbers start to drift a bit. So yes, they might, but we're going to be terribly far away from each other. So the chance of coincidence of intelligent life simultaneously in the universe able to communicate is a very, rather narrow window. So it may happen, and of course, as soon as you say this, I'm sure the Martians will land tomorrow. But the probability from what we know is that it's quite unlikely. And I do rather agree with the suggestion that that shouldn't be a major goal. It's a thing to discuss and to think about, but but physically searching for it when we've got so many amazing life forms on Earth that we don't understand to study, and so much that we could gain from that. It's a very important consideration. I mean, nanoengineering is biology. I mean, the most efficient machines in the world are biological machines. I mean, I think DNA polymerase is 98% efficient as a machine. So there's an enormous amount that we can do for the world, for ourselves, by studying existing biology and using and really thinking about it in engineering terms and beginning to think about nanomachines and the sort of barrier between what we consider currently to be biology and what we consider to be engineering. There's enormous scope there for incredible improvement and development. And I think the resolution of many of the problems that face us as a species. So it seems to me, you know, the inner space, if you like, is still a very good place to look.
Okay. Another quick comment. I think a good thing to be wary about is it's probably true of biology as much as it is of astronomy, and that is that we don't actually know the probability of anything occurring with any sensible degree of accuracy. So our intuition about probabilities is based on things that are very close to equilibrium, where the law of large numbers holds. But in astronomy, we don't know the probability of planets forming or the output from the inflationary universe having particular types of structures. And we can't write down what is the probability of the evolution of life on a planet. These processes are far from equilibrium. They're not governed by simple Gaussian statistics. There was once a formula that became very famous in some circles. It still is, the so-called Drake formula. Tommy Gold used to call it the nonsense formula. So it's this prediction of the number of life forms or inhabited planets there should be. And it's just the product of the number of stars that are right times the number of planetary environments, times the probability of something else happening, times the probability of life persisting, and so on. And it's assumed that all these things are independent and you can just multiply them together to get a final probability. Of course, if you put enough independent things in the line, they're all less than 1, and when you multiply them together, it gets lower and lower and lower. So you shouldn't take seriously formulae of this sort, because these are not independent random events close to equilibrium. What's the probability of a flame? A stable situation far, far from equilibrium. You would have thought it's 0 if you had always just studied Gaussian fluctuations. So in cosmology, you're used to one very large number, the number of planets and sites where life could develop. And some people think, oh, that number's so large in our galaxy, life must evolve somewhere. But I think the biologists have so many pathways that events could follow, so many that lead to dead ends, that they have a very, very small probability to multiply by the very large astronomical probability. Both are really uncertain. The product is even more uncertain. So it's nice to chat about, but you shouldn't take the answer as being the reason to sort of search or not to search, or to develop some big strategy. So these are intrinsically uncertain things. We don't know how life originated in detail on Earth, let alone whether it could develop on the moon of Saturn. So there's lots of places to look. We've seen with planets, for example, it wasn't very long ago before the only planets we knew were the planets in the solar system. Now there's probably way over 1,000. I've stopped counting. There was a time when you used to count how many extrasolar planets there were, but you don't do that anymore. There are thousands of them. Planet formation is a very common process. But the planetary systems, where there's more than one planet, are really odd. They're not as was expected. So in the solar system, the planets all move around on nice circular, almost circular orbits. Supposedly Newton showed they're elliptical and so on, but they're not very elliptical. They're about as elliptical as the circle you draw freehand. They're very close to being circular. And that has great consequences. It means that they're sort of annual variation, as it climatic variation, is rather small. They're always the same rough distance away from the sun. If they're in enormous elliptical orbit, then conditions change dramatically. You freeze out here and then you fry close in. But with, I think, probably only just one exception when I last looked, all these planetary systems that have been found with more than one planet, they're highly eccentric orbits. You know, they come almost grazing the surface of the star and then go far, far away. And you might wonder whether that's got something to do with life. The other thing about the planets, they tend to be rather massive. The way planets form is loads of debris gets sprinkled down, as it were, in the initial process, and then as this planetesimal goes round, it hoovers and sweeps up everything in its orbit, and it gets bigger and bigger and bigger. Eventually, it's hoovered everything up, and it doesn't get any bigger. So if you're in a circular orbit, you hoover everything up, and you reach your maximum size, and that's it. But most of our extrasolar planets we see are really huge, and they're on these elliptical orbits that precess, and they go everywhere, and they never stop hoovering up debris, and the planets just keep getting bigger and bigger and bigger. They never run out of stuff. So we begin to see that there's probably some very interesting, complicated link between the dynamics of the planets, the shapes of the orbits, long-lasting, stable climatic conditions, and so on. So there's a very interesting story, I think, to eventually unfold.
I mean, the obvious sort of critique of that is we see the big planets because they're big. I mean, have we reached the point yet where we can be certain that there aren't smaller planets, or is that still in discussion?
No, we do see planets now down to almost the size of the Earth. So
right.
That was once very true.
Yeah.
Solid rocky planets, that's the key.
Yeah.
Originally they were all big balls of gas and liquid hydrogen.
It seems to me that when you were talking, I think we biologists are quite lucky that we have DNA, actually. So if it's, in a way, it's much easier for us to understand evolution, as Sydney said. So is that a DNA of cosmic evolution?
The DNA of physics is the simple harmonic oscillator. So pretty much everything that's stable just obeys a simple harmonic oscillator equation. No, I think cosmology is much simpler than biology. It's much simpler. So we have Einstein's equations, we can find an exact solution. Things happen very slowly, one at a time. So it's actually much simpler. So, you know, people always have this idea that ultimate huge things like the universe must be more complicated and harder to understand than, you know, things like glass, or it's not the case. So we think we understand the global behavior of the universe really very well, but we don't understand in detail how stars form or how planets form. This is much more complicated. Just like the weather. You know, we can't predict the weather. We can understand the weather in the past quite well. So astronomy has its own horribly complicated things going on in the universe. But the overall expansion is not that complicated. It could have been, but it isn't.
What about, I mean, the other sort of area for discussion these days, which I went to a very interesting lecture on, is, you know, with the title of the lecture is Are We Living in the Matrix? And this was really to do with the problems of sort of the very small, you know, when we have things like quantum coupling and these very difficult phenomena to understand. I mean, does cosmology cross into that area of deep uncertainty?
Yes. I mean, if you go back to that picture of inflation with all those different bubbles where things can fall out differently, in some schemes what can fall out differently from bubble to bubble is not just the density of material, but it's the number of dimensions to space that get large, or the strength of the forces of nature. So much more exotic things. And one way of sort of viewing our visible universe is that string theorists tell us the real world is 10-dimensional, there could be many more dimensions. But for some mysterious reason, our visible universe has had 3 dimensions which inflated, and the others have not. That's one way of viewing it. The others remain fantastically small, but 3 of them inflated, and only 3 in our part of the universe. Again, from a sort of biological view, if you had 4 becoming large, or any number except 3, there can be no atoms and no planets. There's no bound structures. So we shouldn't be very surprised to find that space has 3 dimensions. We couldn't exist if it had any other number of dimensions. So if it's a random process with some bubbles having 3 large dimensions, some 4, some 5, and so on, we would be in one of the 3-dimensional ones. So you can take your choice as to how exotic you want the things in the different bubbles to be. But string theory, it actually tells you how many different options there are. It's about 10 to the power 500. So these are the number of Calabi-Yau manifolds which form the basis for physics in each of the possible outcomes.
Okay, another question from the audience in the back over there.
So, speaking as a biologist, the natural selection as a force towards evolution is something which we think could have contributed to species and diversity and so on. But if this force of biology or life as such, did it come into place only after all this evolution or cosmological evolution happened, or is it something which always was there but not necessarily relevant? Is there any link between the forces of, say, life or biological life as against physical life?
I mean, we imagine biology is more recent, and what's needed for natural selection is rather simple. I mean, you have to have 2 conditions. You have to have reproduction, and then you have to have selection, and then you have to have mutation. So that those, because we can essentially in the laboratory do biological evolution. I mean, we can evolve a green fluorescent protein that's brighter or a different color, and the processes are quite well described. So in that sense, it's an intrinsic feature, really, of the way that biology works, the way that we have, the DNA as the genetic material, that we can have this natural selection. So I think it is very much tied to the evolution of life. I mean, I think it's a very important question. How, in order for life to evolve, that process has to develop quickly. So the key element to thinking about the origin of life has to be how quickly you get to a system that has those properties of evolvability, variation, and selection, because that's what drives the rapid development of different life forms. So it's a very critical question: how do those very basic building blocks assemble to give you a selectable system? And many people are trying to look at that question and try and develop selectable systems.
Yeah, you remember cosmology starts to give you atoms when the universe is a few million years old. I mean, people have posed the question, could you have life based on other interactions? And, so far, what the most reasonable answer is you could not spontaneously evolve something like life based on other interactions. When I was at high school, there were science fiction stories and articles in New Scientist magazine that used to take great interest in the idea of having silicon-based life as an alternate biochemistry. But I think silicon likes to end up as silicon dioxide in the end. It's a rather stable quartz or something. But what's happened, I think, is not silicon chemistry that proved the other life form. It was silicon physics. But that's not spontaneously evolved life. It's had a helping hand from carbon-evolved life. So if you want to have spontaneously evolved life, I've never heard a good argument as to why it would be anything other than carbon atoms. But once you've got carbon-based life, there might be all sorts of other lifelike situations that you could stimulate and create. People have even talked about, once you have intelligent actors in the problem, people have mused about how there might be intelligent control of universes, and even, what the signature might be. Because you remember this internal inflation model where you had the little bubbles, each spontaneously producing other bubbles, and different ones, might have different values of some of the constants of nature and so on. But suppose you could simulate that in the laboratory. You could initiate those phase transitions that produce another inflating bubble. You wouldn't see anything, it would just disappear away at the speed of light. But you could engineer what the properties would be of that universe. And somebody once mused, maybe the strange coincidences in our universe is evidence that it's the long-term result of this gradual tuning. Yeah, so the intelligent manipulation of universes, is a very awkward problem. Once you allow that into the game, that there's a very, very advanced civilization that's actually able to manipulate certain aspects of the structure of the universe at the, most microscopic space-time physics level, then you can't predict the future anymore.
And we are in fact living in the matrix.
Yeah. Other questions? Yes, over there and over there. The gentleman over there first? Oh, you. Okay, all right.
Hi. We all understand that mostly there's first a physics and then followed by chemistry. I think in that order of evolution of perhaps the universe as well as science. And then there's biology, which means that the physics and chemistry is probably closer together, and chemistry and biology is closer together. I remember the Penzias and Wilson experiment where they had to clean out a lot of bird shit from the antenna just to make sure that those things were not affecting results. I always get this feeling that physicists were the ones who didn't want to get their hands dirty, but the biologists were the ones who were a little poor at math. So having said that, is there somewhere in between, perhaps where these two sciences can combine even closer than what the physics and chemistry is together, and chemistry and biology is together, and perhaps the things like a bioentanglement theory and physics that might spring a new science and new discoveries?
Who would like to take that?
I'm not sure I understood the question, but I think to understand biology, it's all based on chemistry and physics. Maybe primarily on chemistry. Physics is harder because we don't know how to do the experiments, right?
Yeah. And we're no good at maths, that's for sure.
Yeah.
But I mean, there are these areas that are fascinating, and then one of them is biology aware of quantum physics, for example, and people are looking at those problems now. So some of the ideas about the sense of smell, some of the ideas about directionality mechanisms in birds, they do begin to probe that area. So people, and of course it's fascinating if that's possible. I mean, what biology does is remarkable in terms of chemistry. So chemical reactions that are almost impossible happen every day because of biology, because of enzymes. So it is a very interesting area. And I think every time you cross disciplines, you have a great opportunity to make really big impacts. So the more that people think across domains, the more likely they are to come up with something very original. So, who knows what we could achieve? But it's not inconceivable to look into those areas and think, will there be a quantum manipulation that uses a biological tool? It's not impossible to think.
Okay. Another question.
I mean, there's this idea of whether there's a quantum biology. I mean, lots of people take this seriously and work on it. I mean, one area I remember being interested in long ago, that everyone has heard of the Heisenberg uncertainty principle in quantum mechanics. But there is another type of uncertainty principle that's not so well known that was noted by Wigner. And it's an inequality that tells you the size of the smallest clock. You see, the uncertainty principle places a limit on a single measurement. But if you want a clock, you've got to make repeated measurements. And this is a much stronger condition on a quantum state. And so you end up with another fundamental inequality, which is a bit like the the energy-time inequality, but multiplied by the ratio of the smallest time interval that your clock can measure, multiplied by the running time that you want it to operate. And when you use this inequality to look at small bacteria, things that have some sort of cycle, some time cycle, you find this gives you a natural understanding of what the smallest size is. They're the smallest things that could have a stable, long-time life cycle of some sort of clock. So there are situations where quantum mechanics impinges on life, but I would be surprised if quantum mechanics played any crucial role, say, in the workings of the brain or something like that. I mean, your list of different subjects, I think a nice way to go is to start with mathematics, right? Go to physics, chemistry, biochemistry, biology, then you're up to psychology, psychiatry. And what's interesting about the spectrum is that there's only two subjects in it which can think about themselves. On the one hand, there's mathematics at one end. Thanks to Gödel, mathematics is able to make statements about mathematics. So Gödel, showed there was a one-to-one mapping between numbers and statements about numbers. And then at the other end, there's psychology, which is a subject that can make statements about psychologists. But the subjects in between are not really like that. So there's this curious link between the maths at one end and the psychologists at the other end. That they're the only subjects that can speak about themselves.
Okay. There's the young man over there who has already the microphone.
Okay, so I have two questions regarding your talk. So the first one is regarding evolution, and the second one is regarding the universe. So for the first one, it's in reference to what he talked about regarding natural selection. And this example just came to my mind, which is basically a moth that evolved to have its underwings like having an eye pattern that makes it look like an owl or something. Yeah, and then when the predator wants to attack it, it just flashes open its wings, and then the eye scares the predator away. So I was just wondering, how can natural selection be such a coincidence? It's like at first the wings are like totally dull, and then it evolves into an intricate natural artwork. Yeah, so how is it that the different sequences of mutations can actually convert dull wings into something so intricate and so exact that it's able to scare away the predator? And also, if the evolution really did take place, then how is it that it actually managed to evolve this much and so drastically with thousands and millions of mutations before the entire population got wiped out by its predators? Okay. Yeah, and for the second question, it's regarding evolution of the universe. Yeah, so I was just, in reference to the slide, we actually said that the temperature would decrease with the volume of the universe. So given that...
Can you ask the question so that we can...
wait, like later. As in later.
Answer the first one first.
Yeah. Then you come to the next one.
I mean, I think as Sydney said, I think the moths that didn't have the right pattern would just be eaten, and so they're out of the question, and it's only by survival, right? It's just, it is truly natural selection. So you evolve by chance, and then you have the ones that survive because they can frighten away the prey.
I think one of the, well, it's not an error, but one of the differences in how we think things work is that a small mutation can have a very big effect. So, in human beings, a single base pair change in their DNA will affect whether they get cancer or not to an enormous extent. So you have that one error, and everybody in your family will get cancer by the age of 30. So that tells you, mutation can, in a single base change. So mutation can be hugely powerful. So we, because of the way biology can amplify effects, we need to be very aware of the range of things that can be generated, and then natural selection can happen on that range. So it's a mistake to think that you might need thousands of mutations to make that structure. 2 mutations might be enough, and that's why it works. And that's because the structure of the butterfly wing is highly repetitive, and so small changes have a very big effect. In fact, in biology, we use the Drosophila eye as a very powerful genetic system because it's such an ordered structure that it's very sensitive to mutation. So single changes can make the eye look completely different in shape and form from a single change.
One amateur biological comment. Arctic hares are interesting to show how these sorts of colour adaptations sometimes can go wrong. You can't predict what will happen. So the Arctic hare sort of stays white when all the snow is there. This is very good camouflage. And then it gradually starts to turn brown, because the snow is going to melt, and then it needs different type of camouflage. But sometimes, things are, it gets a bit colder for longer than is expected. And they find themselves brown when there's still snow on the ground. And they're much more easily caught by predators than they would otherwise have been. So, this is one of the awkward random features of the environment, that, it's not taking its orders exactly from what the climate is going to be today or tomorrow, and it may find itself caught out by change in the environment on a timescale quicker than it can respond to. And it finds itself, in a worse state than if it was sort of a beige colour all the time, which must have been that must have been an optimal issue for it. Do you want to be in between, or do you want to be white turning to brown?
Did you have another question?
Okay, so yeah, thank you very much for your explanation. So my second question is regarding evolution of the universe. So one of the slides just now posited that the temperature of the universe decreases with its volume. And given that it currently stands at 3 Kelvin, would it, and it's expanding at an accelerating rate, so will there be a time when actually the average temperature is so low that even the solar system, it won't be warm enough to sustain itself? And another slide also posited that in the future, like 100 billion years later, cosmologists won't have any galaxies to study because they would have disappeared beyond the event horizon. But then how could we guarantee that within the next 100 billion years, more galaxies wouldn't form nearer to our solar system such that we could study them, if so many of them could have formed within the first 14 billion years?
Let me answer the second question first. Once the universe starts accelerating, there's no further formation of galaxies and stars. So the expansion is so rapid that material, can't escape the effect of the expansion and condense to form galaxies. Even if it could, you couldn't make any stars because all the raw material, the gas and dust that's used to make stars, is already used up. So there are galaxies today where star formation is extinct. Elliptical type galaxies, it's already complete. So there will be an end to the formation of galaxies and stars in the future. And your other question was just about the temperature. So the temperature we talked about was the temperature of that black body radiation. So it's 3 degrees of absolute zero everywhere, and it will keep falling, like 1 over the size of the universe. And when the universe accelerates, the size grows exponentially with time. So the radiation temperature will head towards absolute zero, gradually asymptoting towards it. But the local temperature in this room is not 3 degrees. Okay, so locally on a planet or in a star, you can have a much higher temperature. As all the stars die, those temperatures will fall, they will get lower and lower and lower, and ultimately they will be as low as that background radiation temperature. So
Okay.
nuclear reactions will come to an end.
We have time for 2 more questions.
Thanks for this really great talk, really exciting. I'm not sure if the question actually making sense, but I'll give it a try. So we know that human civilization is only maybe 1,000 years, and the science we know today is only 100 years. But today we're talking about things that is billions of years ago and billions of years from now. So how much do we know? Or how much of the thing we call science today actually still makes sense in 200 years' time?
Who wants to answer this?
I think we can all have a go. I mean, you have to be very careful about language here. So, and Newton still makes sense. His description of the world is very powerful and very useful. And if we still only had that description, we could still safely navigate. So the science, is very powerful and very important. Is it completely correct? No, because Einstein's studies show us that at a certain level, Newtonian physics is not sufficiently accurate. And I think that's really how science develops. So we build on what's there already, and we refine and improve what we know. And I think, is it that those things will be absolutely proven to be wrong? No, I don't think so. I don't, So I mean, but that's really the discussion. But my sense is that we build on firm foundation, and of course we make mistakes, and we usually make mistakes as we get into the more exotic areas of science. But the core of the scientific method has stood us in very good stead, and the process of sort of experimentation and test is very important. So even if you have a very exotic theory, then you have to build a very large ring in a mountain in Switzerland to show you're right or wrong. But I mean, nevertheless, you get there. So,
Yeah, there's an unfortunate view of science which became very prevalent due to Thomas Kuhn, who was a historian of science, really, rather than a philosopher of science. And it was these sort of Kuhnian revolutions, that the way science progressed was some theory being overthrown in a revolution and replaced by another one. And Kuhn, I think, emphasized that idea because a lot of his research had been on the so-called Copernican revolution, which replaced Ptolemaic astronomy. And there's probably a good argument that this was an overthrow revolution of that sort. But developments in science today are not like that. There are no overthrow revolutions in, I think, physics today. That what happens, as it's just stressed, that if you look at Newtonian gravity, okay, it's not true. Okay, Newtonian gravity is not a 100% correct theory. We know that. But it was not overthrown and replaced by general relativity. The general relativity extends the applicability of Newtonian theory into situations where speeds are close to the speed of light and gravitational fields are very strong. So if you look at general relativity and you take the limit of slow speeds and weak gravitational fields, it becomes Newtonian gravity. And similarly, you look at quantum mechanics and you take the limit of things which are large compared to their quantum wavelength, and the theory turns, for the mean values, turns out to be the same as Newtonian mechanics. So this type of structure, where we say theories are commensurate with other theories, I think is an indication of a type of mature scientific development. So string theory, for example, it was so exciting to people because when you looked in a particular limit of this theory, where the string tension became small, so all the strings became points, and you looked at the string spectrum, there was a particle called a graviton which obeyed exactly in the low energy limit Einstein's equations of general relativity. So this is the structure of physics that we recognize, that new theories contain the old ones as limiting cases. So there will undoubtedly be, there is a quantum gravity theory that we don't know, but it will contain general relativity as the low energy limit. And the low velocity limit of general relativity is Newtonian gravity. And in 1,000 years' time, if there are schools of engineering, they will be studying Newton's theory of gravity in just the same way that we study today, probably with a lot more computer simulation. So there will be brand new things, but this way things evolve is interesting. I remember in 2000 there was a competition in Britain. The public had to vote the greatest Briton. You know, so the candidates, there was Newton, Shakespeare, Princess Diana, Cliff Richard. You know, these are all the Winston Churchill. He was the winner in the end, and Brunel was second, the great engineer. But I always remember that there was a journalist who had to give a sort of summary of Newton's case, and he said, you know, Newton had a very strong case, but it's been shown his theories are wrong. You see, so this betrayed this sort of lack of understanding of what it meant to be wrong. But whereas in fact you contained a huge part of the truth. Yeah, so Churchill was second, Brunel was first, Brunel was second. Thanks to a massive campaign by students at Brunel University.
Okay.
Who perfected the art of multiple voting.
All right.
Where were they during the Brexit vote?
You still want to make a comment?
And I think the way I think science is going, even in my lifetime, I think one difference now than 100 or 200 years ago, it's very hypothesis-driven in those days, or even the birth of molecular biology is very hypothesis-driven. Now, through technology development, we have this ability to collect huge data. So it's really changing the nature of the way we do our science, right? We don't necessarily need to have a hypothesis or test a theory, but we can do experiment and collect the data. Then, of course, the big question is what you do with that data. How do you turn that into knowledge, right? But I think we agree as biologists. The way, even in my lifetime, we went about asking questions has changed dramatically.
All right.
My guess
can we make
is that
it short
what
now?
you'll do in the future is, a big impact on many areas of science is simulation. Massive computational capability. You can simulate almost the formation of whole galaxies in huge detail. And, this is only going to get bigger and better. And I presume in biology there's going to be massive simulation capability, to study vast, long timescale processes, artificially accelerated.
All right. I think this was a good... Is there an urgent thing you still want to say, Daniel? Okay. And I think we'll have to stop here. This is 6 o'clock. I would like to thank the three people in the panel, and especially Daniela and David, because they were totally unprepared to do this. So was I, actually. But so please give them a loud applause.